Hey, how's it going everyone? Welcome to this video. Today we're going to have a look at limits, continuity, and differentiability. So last chapter we touched on the concept of limits. Just as a bit of a recap, we've got for any function y equals f of x, we had the statement, the limit as x approaches a for the function f of x equals L. Means that as the x values approach the value a, so as x approaches a, the y values approach, oops, approach the value L. So as x approaches a, y approaches L. We can write that as x approaches a, then y approaches L. Similar things. So a limit is only concerned with the behavior of a function as it approaches a particular point and not with its behavior at the point. So we're more concerned on what happens on just as we approach the point A on the left, what happens as we approach the point A on the right, but not particularly the point at A itself. Because so if we had the point f of A, it might not even exist. So we're interested as what happens just before we get to A. Um, we had a look at last time from first principles when we're looking at the value h as it approaches 0, and it could be the function 2xh plus h squared over h. And we said, well, from this we can't substitute h equals 0 exactly into this equation because we'd be dividing by 0. So we need to do something first, and that was by factoring and doing some cancelling. So we said if we have h out the front for the function, we'll have 2x plus h over h. They end up cancelling. So we ended up with the limit as h approaches 0 for 2x plus h. We've got a simpler equation now, and we can then sub in h equal to 0. So when h is 0, we get 2x. Okay, so we get a bit of a table that we can refer to. So to evaluate the limit of a function as x approaches a, we need, if the function is well behaved, then we can sub the value x equals that number into the equation. If it's not, then we needed to obtain a well-behaved function. By simplifying and cancelling. The third option, if it's not possible, so if we can't simplify that, the equation from step 2, then the limit does not exist. So just going on to an example, so calculate the following where possible, the following limits. So we've got the limit as x approaches 2, we've got 4x plus 3. So for x plus 3, we've got a well-behaved function, so we can just go ahead and sub x equals 2 into the equation. So we get 4 times 2 plus 3. 4 times 2 is 8, plus 3, so we get 11. The second one, we've got the limit as x approaches minus 1. For x squared, take 1 over x plus 1. X squared take 1, I can actually write as x plus 1, x minus 1. So just going back to quadratics, I won't go through how we do that in this video. If you're unsure, please ask. So you got top and bottom, they can cancel. So we get the limit as x approaches minus 1 of x take 1. So now we can sub x equals minus 1 into it, and if we do that, minus 1 take 1 equals minus 2. Third option, we've got the limit as x approaches 1, 1 over x take 1. X take 1 I can't actually simplify, and 1 over it. I'm not able to sub in 1 because I'd have dividing by 0, so this is not defined. So I can't find the limit for that function. The next thing I just elaborated from the first slide, we've got left and right limits. For a left limit, I'm just concerned for the function what happens to the limit from the right of that point. So what I'm meaning is if I've got x squared and I've got the point A, I might not be interested at the point of f of A, sorry. So I might not be interested at that point, but I'm interested what happens as I get closer to that point. And I get the limits, what happens on the left, and also what happens on the right. And do they converge to the same point? Well, for a quadratic, yes, they will, but we will have a look at other functions where they don't. So when we're talking about the left limit, what happens to the point on the left? Well, we're actually starting on the negative points, all our negative x values. So we can say the limit on the left, meaning L negative, is going to be the limit as x approaches our value a from the left, and we put that minus sign there for our function f of x. And then for the right, we're coming in from the positive numbers, so we're going to be, sorry, that should be an L. Our limit from the positive numbers, meaning from the right. And same thing, except now we're going to have a little plus above it for the limit for f of x. So for the example, I might have this function here. So I've got two straight lines, and they stop at the point 2, x equals 2, and I'm interested at what happens on the left and the right at that point. Well, for this example, I'm going to say that point there is going to be 4, and that's going to be 6. So I say, from the left-hand side, so L minus, I get the limit as x approaches 2 from the left for f of x. So what I'm saying is, from the left hand side, all my negative numbers, I'm going along, and I go up the line, and I'm reaching the point 4. So I'm heading towards that point 4. And I do the same thing, except now I'm looking at from the right of 2. So meaning from the positive numbers, I go along my function, and I'm getting closer and closer to 6. And as you notice, at the point 2, I'm not particularly interested at what happens at that exact point, but as I get closer, I'm getting closer to 2 different numbers. And because I'm getting 2 different numbers, the limit for x approaching 2 does not exist. So when I have the limit at x approaching 2, it does not exist because I've got 2 different points for the left-hand values and the right-hand values. So we get some more definitions. So if a function is continuous at a point where x equals a, so if the function is continuous at x equals a, then we can say f of a exists. We can say the limit as x approaches a for f of x exists, and the limit as f approaches a for f of x is therefore the value f of a. So for a function to be continuous, essentially there will be no break in its graph. So from the past example, we had a look at a quadratic. For a quadratic with no restrictions on its domain or range, essentially we start from one point, so the leftmost point, and if I follow my pen over the line and I go all the way across without having to lift up my pen at any point, then it is continuous. However, if we had a look at the other example, I do the same thing. So I start from the left and I use my pen and I trace it along the line. I get to the point at x equals 2 and I have to lift my pen and go to the other spots up there. So that means it's not continuous. So this is continuous because I can't lift my pen up, or I don't need to for the whole graph, whereas this one I have to lift my points up, my pen at x equals 2 to reach that top point there. So that indicates that it's not continuous. So worked example 2, we've got a function defined as f of x is the hybrid function x for x is less than 1. We've got f of x equals 1 for the value when x is equal to 1, and x squared for when x is greater than 1. So first step, I need to calculate the limit as x approaches 1. So I'm calculating the limit as x approaches 1 for f of x. So I can draw it. Most of the time it's useful, but don't need to, particularly in this situation. So I'm looking at the values for when the limit on the left. I get the limit as x approaches 1 from the left, meaning negative, for f of x. And if I do that from the left, I'm looking at the leftmost points are my negative numbers, and that's f of x equals x. So I get the limit as x approaches 1, the function is x, and if I do that, I get the point 1. So subbing in 1 for x, I get 1. Doing the same thing but for the right, so on the right I'm looking at the positive numbers, so x is greater than 1, so the limit as x approaches 1 from the right of f of x is the same as x approaches 1 from the right of x squared. And if I do that, I get, I can sub that in at x equals 1, so I get 1. Okay, they're the same numbers. I just need to check that final step. What happens at f of 1? And if I do that, when f is equal to 1, I get the value 1. So because all three values are the same, essentially what I'm saying is f of a exists, f of x as x approaches a exists, and we get the value f of approaches a for, yeah. So because all three are equal, I can say that it is continuous, which lends itself to part B. So I've just said that the graph is continuous at x equals 1, and I can illustrate that by drawing the graph. So the function f of x equals x for less than 1, so at 1 I say that we get that straight line, but stops at the point 1, and it's less than, so it's an open circle. I get the function f of x equals 1. Oops, sorry, that's minus 1. So I keep going up until positive 1. Now, at positive 1, I have the line f of x equals 1, so I get a straight line at that point. Oh, sorry, no. Sorry, at f of x at 1, I get to the point 1, meaning I basically colour in that circle. And then the last one, as x is greater than 1, I get the quadratic as shown. So as you can see, because I've filled in all the spots, even though it's a bit of a strange graph, I don't need to lift my pen up at any time, meaning that it is continuous. Part B, for the function, we've got g of x equals x squared plus x over x plus 1. State the maximum domain. So the maximum domain for that is going to be, well, basically all real numbers except for when x plus 1 is equal to 0. So essentially all numbers when x is not equal to 1. So all real numbers except for the point, sorry, at minus 1. It asks to calculate the limit as x approaches that number at minus 1 for g of x. So I get the limit as x approaches minus 1 for x squared plus x over x plus 1. As we said before, you need to try and simplify it if we can, because I've got this value down here So I can take x as a factor. I'd have x plus 1 over x plus 1. Okay, I've got 1 on the top, 1 on the bottom. They cancel. So I get the limit as x approaches minus 1 for x. I've got a simple function. I can sub in x equals minus 1. I get the value minus 1. Part 3, explain why the function is not continuous at minus 1. So the domain of the function is all real numbers except for minus 1. So g of minus 1 does not exist. So therefore, it's failed one of the conditions, as we said, for continuality. We can't sub in g of that number, so it is not continuous. Part 4, sketch the graph of g of x. So, as we said before, or as we calculated before, I can actually simplify this as g of x is actually equal to x, the straight line x, but it is not it's not defined for x equals minus 1. So therefore, the graph of g of x is the graph y equals x, and for x not equal to minus 1. So I can basically got my set of axes. It's just the line y equals x, except at minus 1 I'm going to have a missing point. And that's basically the graph of g of x. Just talking back to differentiability. If the derivative function has a limit definition, and as a limit exists only if the limit from the left equals the limit from the right, to test whether a continuous function is differentiable in its domain, the derivative of x equals a on the left must equal the derivative of x equals a from the right. So basically, um, a function is differentiable at at x equals a if f is continuous, if it's continuous at x equals a, and if f, the derivative of a from the left should be just a, so the derivative of a from the left is the same as the derivative of a from the right. So they both have to be continuous at the same spot. If we have a look at the hybrid function that looks like this, we've got a sharp point. Basically, rule of thumb, if you have a sharp point, it's not going to be differentiable. But in terms of this equation here, I've got the derivative of a from the left is going to have a positive gradient. Remember, derivatives just look at the gradient. So at that point, I'm going to have a positive gradient on the left, whereas I'm going to have a negative gradient when I look at that on the right. So because I get two different numbers here, it's not going to be differentiable. Essentially, if you have a point, a sharp point like that, it's not differentiable, uh, just as a rule of thumb. So the last example we're going to have a look at, worked example 3, the function defined f of x is the hybrid x for x is less than 1 and x squared for x is greater than 1 is continuous at x equals 1. So part A, test whether the function is differentiable at x equals 1. So again, as I said from the past slide, we've got f of x from the left is going to be x. So our derivative of x from the left is going to be 1. So therefore f dash of x from the left is equal to 1. And then from the right I have f of x is going to be x squared. F dash of x is going to be 2x at the point. Um, sorry, that should be sorry. When you put 1 in, you get 1. So f dash of 1 from the right is going to be 2. 2 times 1 is 2. Because the left does not equal the right, it is not differentiable at the point x equals 1. Part B, give the rule for f dash of x, stating its domain and sketch the graph of the derivative. So each branch of this function is a polynomial, so the derivative is going to be, so as a whole, basically part A says I can't differentiate this whole function altogether. However, I can differentiate it individually by parts. So just looking at the top bit, I can differentiate that. It is continuous for all values less than 1. So the derivative of that is going to be what we discovered down here is just equal to 1. So I can say my derivative is going to be a hybrid function, 1 for the values x is less than 1, and I'm going to have 2x for the values x is greater than 1. And if I sketch that, f of x is going to be 1 for less than 1. So it's going to be a straight line there, open circle, and then it's going to be 2x for x is greater than 1. And essentially I start at that point there. So that's 13.2, limits, continuity and differentiability. Thanks for watching.